My name is Boaz Shor. I work at Tabola. We are a recommendation system. Usually when you go to publishers' websites to read the news, at the bottom you have, you may read more. That's us. That's us. Okay. So today I'm going to talk to you about a specific project we had regarding semantic similarity between articles. And let's start by taking a look at some of the articles and trying to understand what we want to establish. So there are many levels of similarity, and we want to differentiate between different levels of semantic similarity between the articles. You can see here that we have two articles about Trump and about Kim Jong-un. And these two articles speak about the same meeting between Trump and Kim, and they're basically talking about the same article. On my left, you can see different levels of similarity. For instance, we can be talking about two matches in the Wimbledon tournament, or we can talk about two different articles regarding Trump's problems with the Ukraine, and we want to model this similarity in some way. So today, basically, what I'm going to talk about is our problem definition. What was our first step out of the box approach to try and tackle this problem? How we tried to do it better, and then some results. So basically, what we want or what we need is something that can get two articles, measure the similarity or the levels of similarity between these articles, and if I have that, I can use it in order to predict CTR. I can use it for finding content relatedness, deduplicate stories, user profiling, finding similar articles to the user's history, and much more. And basically, that's what we want to achieve. So if this was my problem when I approached it initially, the question is, what is the first step I can take in order to try and solve this issue? So the first thing we did is trying to find already pre-trained language models online. We tried many different types of language models. We passed the two texts of the articles through these language models. We got an embedding. If someone doesn't know, embedding is basically a vector of numbers representing the text. And from that, we wanted to calculate the similarity score. Specifically, in this talk, I'm going to talk about cosine similarity as the distance function, but there are many different options. Okay, so after we did that, we wanted to do some sort of sanity. We tried to understand if what we have is worth something or not. So what was our first approach? So first of all, we took pairs of articles, lots of them, okay? And we passed them through the language model, calculated the embedding, and we calculated the cosine similarity on those embeddings. The first thing we did is look at the cosine similarity distribution. Each of these models creates a different cosine similarity distribution, but just from taking a look at these distributions, you don't learn much, okay? I have a different distribution to LSTM versus bag of words versus BERT, but I still don't know if it's good or bad. Then we started to take just pairs that we had an intuition about how similar they are, like these two articles that both talk about the Premier League, but totally different subjects. And we tried to see what's the percentile of the cosine similarity through the distribution. So just to get a sense, in the bag of words, if we're in the 90th percentile for these two arguments, so this is the distribution of the bag of words, the 90th percentile will be at the end of it. If we're looking at the LSTM and we're in the 10th percentile, it's around here. So we can get initial feeling about how well these models perform and does it make sense to us. Basically, our initial thoughts were, okay, we have something, but it's still not good enough, and we want to improve it. So the big question is, how can we improve it? So what we wanted to do is fine-tune these pre-trained models and improve their transformation into the embedding space in order to get better cosine similarities that more represents what we think about how close semantically these articles are. Okay, what we chose is an architecture very well known, which is a Siamese network. Okay, in a Siamese network, you have two identical subnets, which are basically the same model. They share the weights. Okay, and we pass each of the items through these language models. We calculate the embeddings, calculate the distance, and basically what we have here is some sort of loss that will try and help us achieve our goal, and the label data. Like I said, today I'm going to talk about only the distance function of cosine similarity, and specifically I want to talk about BERT. So the big main question marks we still have is what loss should we use, and how do we get the data, and how to label the data. And it also depends on what approach we want to take. Okay, so first of all, we needed to choose out of the many different levels of similarity, one we wanted to tackle, and we wanted to tackle the related story. I want to find which two stories are related, and in a bigger aspect, we want to find different levels of similarity and identify them. So first of all, the data, which is basically the pain for all of us, I think, when we work on data science. Collecting the data is one terrible thing to do. So we started by trying to use crowdsourcing websites like mTurk and others. We also in Taboola have live editors, newspaper editors we try to send batches of data to and wanted them to annotate it. The big problem is it wasn't scalable. We couldn't get enough data. The crowdsourcing just costs too much to get enough data, especially when you talk about BERT and it has a very big number of weights. And if you want to fine-tune it and really move the needle, you need enough data, okay? And then we tried to look around. We work with news publishers. Many news publishers around the world already has a widget in their website on a specific article saying these are the related articles. Today, the way they do it is a human editor picks the related items. We said, that's amazing. We have data. Let's crawl. Let's collect all these widgets, and we have at least one level of similarity. So here's an example. You have an article, and you have the related widget inside of it. And we found it in many different publishers. And we said, okay, if I'll go and scrape all this data, I have a lot of data which basically represents items which are related. They're semantically similar. But it's still not enough in order to fine-tune BERT. We need more data. We need at least negative examples, or if we want different levels of similarity, we want more. So we decided to go with 3 levels of similarity. So these are similar, related. The next one, we took, publishers usually have something called topics or channels, where they give you just sports, just entertainment. So we said, okay, let's take one of these topics and choose 2 random items from that specific topic. Then we'll have something, let's say 2 items related to NBA. They'll probably be somewhat related, but not as related as the related articles. So we have another level of similarity. And the last one, we said, let's take the entire corpus and choose 2 random items out of it, and then we'll have very different articles. So we basically created 3 levels of semantic similar data by crawling the first, which is related, randomly choosing items from the same topic, which was the medium level of similarity, and choosing 2 random items from the general corpus, which were totally unrelated. Now that we have our data, we want to think about this is the data we have. We still haven't labeled it because it depends what we want to do with it. Now we need to think about the loss. Now basically we looked at what's around, and we saw that there are 2 main approaches. One is classification. There, my labels can be just related, same topic, and unrelated. I don't need to do anything special, and I'll try to classify each item to one of the clusters. The second family of losses we looked at was regression and ordinal regression. I'll say it in a word. Why ordinal regression? Because our labels basically are three constant labels on the range. If you remember, regression is trying to predict a line, a straight line. So we have some sort of range, and all of our data is 1, 2, or 3, and we have nothing in between. So this definition of a problem, similar to if you have, I don't know, stars on movies in Netflix, is a problem defined as ordinal regression. So we tried to choose or to test many different losses that are related to regression and to ordinal regression and to multi-class classification. And empirically, we chose the one that gave us the best results in our initial test. So basically, let's talk about the results a little bit. So the KPI we chose in order to measure how well we do is calculate the AUC of the separation between the labels. How well do we separate these labels? What you're seeing now is the AUC results for the 3 pre-trained models we tested, okay? And you can see here that BERT managed to separate each of the different levels much better than its components. And that's why we chose to continue working with BERT and try to fine-tune it. Then we tried the classification versus the regression. Here, what I'm showing you here is our best result for classification, our best result for regression, and the pre-trained, which is in the green column. And you can see that the regression approach gave us the best results. By the way, if you read a little bit of articles regarding this subject, you will see that usually regression works a little bit better than classification for these types of problems. Okay, so when I say regression, which loss am I talking about specifically? So the one that works best for us was the simplest one, MSC, mean square loss. Basically what you do when you look at this MSC function, you see that you have an average of the square difference between the labels and what your model predicted. Now, if we try to think about what does my model predict currently, we pass 2 sentences through some sort of language model, specifically BERT. We get the embeddings and we calculate cosine similarity. So my label that I predicted is the cosine similarity result that I got. And I need now to think about how to label my data in order for these 2 y and y hat to be on the same scale so the MSC can do its job. Basically, cosine similarity is in the range of -1 and 1 in generic problems. In my world, empirically, we looked at many, many pairs, and we saw that rarely you see any cosine similarity below 0. There's no real, let's call it opposites in language, because men and women, even though it sounds opposite to us, BERT, we look at it like they're very close. Why? Because they're used in the same way in the text and in the speech. So we saw that 99.9% of our examples are between the range of 0 and 1, and we said, okay, let's label our data in the range between 0 and 1. I have 3 labels. So we started with 0, half, and 1. And we said, let's try and see how well it goes. Okay, so what you're looking at now is the cosine similarity distribution across an evaluation data set comprised of equal amounts of each of our labels. On the blue is the 1, which are 2 random non-similar items, okay? In the orange is the same topic, the medium ones. And on the left, my left, you have the semantic similar one. And when you look at the results of the pre-trained BERT, you can see they overlap. They overlap a lot. Our ability to separate between the labels is not very good. So we took our data that we collected and started fine-tuning using the architecture we talked about, meaning the Siamese network with the MSC loss. And what we got is what you see on your left. You can see here that we have the one going very much towards 0, the non-similar. The semantic similar goes very much towards 1, and the twos, which are the same topic, they get spread around. Now, the separation is much better, but it's still not very good. And because the intuition of basically what it did, it was spread the cosine similarity between the ranges we gave it, we said, okay, let's try an hyperparameter tune on that exactly. Let's try many different labelings in the range of 0 and 1 and see what gives us the best results. After hyperparameter tuning, here on the left is the 0, half, and 1, and I'm sorry, on the right, and on the left is 0.4, 0.6, and 0.8. You can see here 3 beautiful normal distributions. The separation is much, much better. And this was specifically true for the English version of BERT base, okay? And that's the model we chose to go with and what we're using today in production. In German, the story was a little bit different. There is a BERT specifically trained on German data. Look at its pre-trained, okay? On my right, your left. Here, they just overlap. It looks like they're all in the same space between 0, 9, and 1. When I try the trick of 1, half, and 0, you can see that they spread around. Of course, they separate much better, but it's still not there. Then we tried to hyperparameter tune, and luckily, I think, we got to the best results for the same numbers. Here, we got a little bit... we had some problems. Because of the initial state of the German BERT, we had a problem converging. And here we had to also play with the learning rate in order for it not to get stuck in local minimas or not get to local minimas and converge exactly where we want. And you can see that the 3 normal distributions are exactly around 0.4, 0.6, and 0.8. And it really goes where we want it to. So we also understood what happens when we fine-tune BERT on the cosine similarity distribution, and we managed to do it using some hyperparameter tuning on the learning rate and different parameters along that BERT uses. Okay, so basically we talked about the problem definition. We said what was our initial approach, how we wanted to tackle it. We talked about how to take it from there, going over to fine-tune the models, and eventually the results. Today, we are serving it in production. Our system answers between 700,000 and 1 million calls per second. And it works pretty well. And we're still working on improving it further, collecting better data, which is the main problem, I think, that we all face, and tuning it much better to get even better results. Thank you.